the start that I like to talk and I like to discuss with you today, we have around 1 hour. It is the last topic, which is the column design. The purpose of the column design, we have two issues that we need to discuss. One, we look at the stocky column, which is quite similar to what you did for the reinforced concrete and also for the steel design. So you have to calculate what's called as an interaction diagram. The interaction diagram is a combination of the axial force and also the bending moment that applies to the cross section, because normally the column doesn't take the full axial force. It has to take in the combination of the bending moment as well. So that's why we need the interaction diagram to check your capacities. And more likely we can obtain the interaction diagram by varying the neutral axis depth, right? We call as a plastic neutral axis. And I will discuss about this in details. And next week, I will come and talk about how you just find some of the factors to take into account, right? When we have these factors, it will magnify the value of the applied force, right? We call them, we have this factor in the reinforced concrete design, and we have this factor also for the steel design. We use the same concept as those. So that's why the discussion of the cylinder column is not going to be much. But I tell you, for the cylinder column, in terms of the research, is still in the open areas, because the behavior of the columns, either the composite or the steel column for the long columns, especially for the composite, is still quite new, right? So we need some extensive design or the research on this to make it more precise. But in the code that I come and share with you, just about how we can approximate them. Okay. This is the note. You might see this is my handwriting. This is when I was a postgrad student back in 2002, which is about 20 years ago, right? This is the time that I start to be introduced to the concept of the composite column. So this is the history. We have the history of the composite column more than 100 years now, and still it's not quite popularly used in some of the developed country, not the emerging country, right? The developed country, okay, they might use it quite a lot. So what has happened is that we have two of the concept in the composite column. One we call as an encasted, the other we call as the infill. The infill is here, the encasted is on the left-hand side. The difference between the encasted and the infill is as follows. When we have the encasted, we have the steel section, which is the standard steel column. So we normally use the wide flange. We call them as a universal columns, right? Or UC. In the American, they call it a wide flange. But if we talk about in the H columns, if we talk in the Australians or in the European country, they call it as a universal column. But the idea is the same. The section of the column, so the difference between the I section is that we have the thicker of the flange and thicker of the web, right? So if we have the I, this is the H, the I will be the taper type of the shape here, and it's quite slim in the web part of the section. But if we're looking at it, we want to use it for the column, they normally provide quite thick for the web and quite thick for a flange, both the top and the bottom flange. So we call it as a W section, or we call them as a H section, or we call them as a UC, which is the universal column section. And what we know is that the thing when the steel under the compression force is prone to the failures under the buckling. The buckling can be the local buckling, it can be the global buckling or the member buckling as well. The local buckling we call as a section capacity. The global buckling or the member buckling we call them as a member capacity of the column. right? And to prevent this, in the research, which is 100 years ago, they start to have the concrete just cast and envelope through the section of the steel. So they treat the steel member as one of the reinforced part, right? When you have the reinforced concrete slab, so we don't have this. We have the steel design, we have only the steel member in the centers. We combine both of them, right? So when we have the encasted, so they provide the reinforced steel more likely in the corner so that they can cast a slab, so cast the columns, and they insert the steel column in the middle. And in this case, what has happened when you have the encasted concrete column, the benefit that you can grant straight away is the steel member, it doesn't have the local buckling. So it can utilize the maximum capacity of the section. I will discuss about what the difference between the section failures, which is we call as a local buckling, and what is the member failures, right, which is the global buckling. The discussion that we talk today, more likely we will discuss on how we can capture approximate the capacity of the section when it's prone to the what is called the local buckling, and what is meant for the local buckling. You learned it in the steel design already, but I just want to recap very quickly. Right, in terms of the research, there are many areas that you can looking at. For example, when you have two types of the material, the skin of the steel structure, which is the I shape of, sorry, the H column or the universal columns, the shape of them, if I just put here, you can call them. This is the build section, or you can call them as a H section or the UC section, right? So this is all the columns. The surface of column or the steel columns is quite smooth. When the surface is smooth and you cast with the concrete, there it can have the slip between the steel columns and also the concrete by itself. So in terms of the research, they're looking at how can they provide what's it called the friction between this, right? The steel member and also the encasted concrete. And in order to provide the friction, normally what we do, we provide the shear stud similar to what you calculate for what is called the slab or the beams, right? You have to provide the shear stud here, so that is provide the sufficient longitudinal shear transfers between two types of the materials, or you can provide the shear stud on the web as well. So the purpose of the shear stud is to provide the friction so that when you have two types of the material, right, it's come with a different property, starting from the elastic Young modulus, they are different. The Poisson ratio, they are different as well. In these different parameters for the material, under the material properties, what is happening is can make the slip, or it can make some of the interaction of two materials, so that will involve or that will impact on the capacity of the whole column that we're looking at. And this has been put into all the research areas. One other thing is that when you have the reinforced bar here, and more likely is we provide the some partial confinements to the concrete. It doesn't provide the full confinement to the concrete. So that's why when we're looking at the concrete strength, we use the concrete strength, we use the 0.85 F-Francis, which is similar to what you did. Remember that when we calculate the concrete strength under the ultimate strength designs, and if we have the neutral axis here, right, we use up to the strength is equal to 0.003. So this is the concrete strength, right? This is the actual concrete strength, and we approximate them by using the equirectangular diagram. And we use this. We take this as a gamma of dn. This is similar to what you did for the concrete designs, 0.85 prime C's. And what is the value of dn is the start from the top surface of the concrete to the plastic neutral axis, we call as a dn. Right. So when we looking at for the encasted, when we treat the capacities of the concrete, we use just 85% of the capacity, right? But for the steel is will be the fully confined. Sorry, it will be no buckling in the steel. If no buckling in the steel, so what is happened? We can use the full section capacity, right? So this is very good properties that we can have when we have two materials together. But on the other hand, if we have the infills, the concept of the infill is different. You have the open hollow section. In this case, you can have either the square section, which is the SHS, which is the square hollow section, or you can have them as a CHS, which is the circular hollow section. And you just need to fill in the concrete. So you fill in the concrete here, right? This is the filled concrete. Because the concrete has been enveloped by the steel tube, we call it as a tube because this is the closed section. What is happened? The concrete will be fully confined. When it's fully confined, what is happened? Remember, we used to discuss in the first week that we met, the property of the materials. When we're looking at the concrete, the standard property is that it's come up to this point and it reached the crack. You look in the crack section of the concrete, and after that it starts to form the non-linears and it's dropped. Right. When we look at the strength, we take up to the strain of the concrete developed up to the values of 0.003, and we use the areas underneath these diagrams in our calculation, right? That we let me enlarge these diagrams here. Okay, so these diagrams, it is the area which is the purple line here. So we stop at the strain equal to 0.003. So that's why you're having these diagrams. Let me change the colors. Right. No, it's not nice. Sorry. Okay, good now. So the maximum strength of the concrete which is this level, is equal to F prime C, right? But when we do the design, we only use up to 85%. We don't use the full F parameters because we use equivalent rectangular block diagrams. But if you have the fully confinement, the nice property of the fully confinement is that because the concrete has been enclosed, so if we make the cell compact within the concrete matrix, so the behavior of them will be after it reached the ultimate strength, it can go beyond and start to drop here. So we have these nice properties. Remember, when we have this nice property, we have the good ductilities because it can hold a certain value of the stress, right, when the strength keep developing. So that's why we like this type of property. So in this case, what it means the concrete has been fully confined. And if you have this property, so what you do, they allow you, the code allow you to use the concrete strength. When it's fully confined, they allow you to use it to the full strength, which is F prime C. So you use 100%, right, due to the confinement effects. Okay. But when we do the calculation, we still do not allow the concrete to go above 0.003. Okay, this is some of the application that they has used the composite column in the design, and it's very good because it can provide the good ductilities. One of the most popular one that people use in the design is the infill. The infill has been used nowadays for the residential as well. But when the engineer design the infill, they don't talk about the composite action. They just treat them as a steel section or the steel designs, and they don't treat the capacity or then take into account the concrete capacity. So that's why it's quite conservative, because if you decide the concrete section, so if you decide the composite column and you just take the capacity of the steel only, and you don't looking at the capacity of the concrete or the composite action between them, and you just do the construction on that, is quite conservative, right? And this has been used in some of the housing design as well. So they want to obtain the smaller size of the steel, and inside to prevent the buckling, they just pour the concrete in, right? That has been used quite popularly. But in terms of the commercial buildings or the high-rise building, this one is quite popular because it provides a very good or very nice properties with ductilities, right? And it favor for the construction as well. If you read through, they will explain to you that why it gives so many advantages when you use the infill columns, because when you do the construction, right, you just put the hollow section first. The steel hollow section that you just put in the constructions, right, it can sustain the loading for a couple of the floor. When you want to build the floor which is higher, which is more about the floor stack on the top, you can just later pour the concrete in. When the concrete is set and the composite action has been established, then it can gain more strength, right? So this has been very popularly used in the construction, especially for the high-rise building. We have this type of construct in many of the high-rise building in Bangkok as well. You can go, many of the department stores, they use this concept. So they explain the benefit of them, and they just they compare the relative cost. This is used in Sydney. So if you talk about the costing to construct the composite column for the conventional concrete, first, let's say the unit price is equal to 1, right? And if we use the concrete column with the steel erection columns, and we have the encasted, you have the tube filled with the reinforced concrete member, you have the steel tube, but you don't have the reinforced steel in the concrete member, and if you have the full steel column. The most expensive if you just use the steel alone, right? You're looking at the construction cost is about 2 times, right? But if you use the proper design, let's say you're looking at the tube filled with the reinforced concrete. So what it mean inside the concrete, you also apply what is called the rebar inside them as well. If you put the rebar, we normally can have this, and normally people take into account of this. They put the rebar and they put the stirrups here. And then they just have the tube or the rectangular or the circular tube, just enclose them, right? If you have a rebar, if you design like this, you get the most benefit, right? Which is the cost of the construction you're looking at, which is good. And if you just have the concrete infill alone, the cost is not too bad, which is very close to the conventional concrete. But the benefit that you gain from this is, first, you have the fast construction. You also obtain what is called the good ductilities. Why is a fast construction? Because no formwork required. So that's why it's quite popularly used, right? And normally when we talk about it's fast, it can speed up the construction times more than twice, right? When you use a composite designs, especially for the column. I have so many, when I was in Australia, I used to design some of the high-rise building in Sydney. There are many scenarios that when we use the concept of the composite action, right, it can resolve the problems. For example, there is one, and this is the application, right? This is what I discussed to you guys. You can just read it through. This is the building. Normally, I will share the experience with you later. Let me go ahead first. Normally, for the high-rise building, what they do, is depend on the concept of the high-rise building you're looking at, right? If you use a mega column, the mega column is mean you need to design the building with the big size, super big size of the column. In this type of the thing, they normally employ what is called the composite column, and this is non-regular, non-typical composite column, because it has been specially designed for each of the building. Right, you might see the minimum one that they require is that for the high-rise building, they have to provide the shear stud here to prevent the slipping between the concrete and the tube. Remember, when you have the axial force applied to the two of the materials, the Young modulus is different, the Poisson ratio different as well. So that's why when the Young modulus is different, the axial deformation will be different. When you have the different type of the axial deformation, you have the shear transfers to type of the materials. So to prevent the slip, you need to provide what is called the stud, right? To resist, to provide the friction between the concrete matrix and also the tube. And this is the minimum requirement for the high-rise building. When you have the size of the column is very big, you can provide a reinforced bar here, and you provide the shear stud here. Or there are so many different types. For example, right, you have the manhole, right? You have the shear stud, and you've got the steel bar. It depends on how big. If you talk about this, the size of the column is more than 1 meter. right? Then you can fit the orientation of the reinforcement and also the shear stud and the steel tube, which is super big, and this one as well, right? So it depends on the concept how you use, and normally what is happening is this. When you have two types of the materials, why this one is very important, let me explain to you. Because when you have two different types of the materials, for example, I have the concrete, and I have the steel. Okay. And assuming that I have two types of material and I want to make the composite action to each other, so then I attach them. The concrete comes with the Young modulus of EC, the steel comes with the Young modulus of ES. And normally the ES, we're looking at around 8 times of the EC. So what it means, if you're looking at the material properties, you compare the stress and the strain diagrams. For the concrete, this is the initial slope. For the steel, this is the initial slope. Okay, listen to me first. If you're looking at the value of the force, let's say this is the force. This is the axial force, or just to make it precise, I take about the strain, the stress and the strain, right? If we have the similar uniform forces, apply to concrete and steel, right? With the different value of the elastic Young modulus, with the same value of the force, it gives the same values of the stress, right? So stress is the force per unit areas, right? So it gives the same value of the stress which is applied on top of the columns. But because this type of the materials, when it have to resist the stress, and they come with a different value of the strain, the Young modulus. The strain that respond to the stress for the concrete and also for the steel, even under the elastic designs, when we check for even under the elastic designs, you see that the deformation, the strain is determined the deformations by the length, right? The value of the strain that has been developed that with the same stress of the concrete and the steel, they are quite different. The difference is about 8 times as well, right? The steel have less value of the strain. The concrete has more value of, of the strain. So what is happening that we develop a different settlement, right? The shortening in the concrete, not the settlement, the shortening in the materials. So the concrete will deform more than the steel. If it deform more, what is happening when you're looking at the interface between two materials? If I zoom it in, there will be the difference in terms of the shear force. Not the different, the same shear force, but there will exhibit the shear force, right? To make two of the material that can stick to each other, we need this of the shear stud that can take out the shear we call as a longitudinal shear. It's had to resist it by the shear stud. So that's why in most of the high-rise building, the effect of this is so much critical, very much critical. I used to design a building for 40-story. The axial deformation, which is the difference between the steel and the concrete, make a lot different, right? When especially when you want to stack more number of the floor up, so it will load more to the column. So it will enlarge more the different shortening between two types of the material, and this become one of the big issue as well. So that had to be taken into account. But in this lecture, we not go too much detail on this, but I just try to tell you when you're looking at in the drawing, there is the reasons why they provide this type of the components. Okay. When we're looking at the designs of the columns, the first thing of all, we start to looking at what is called the capacity of the squash load. The squash load is mean the full section taking the full compressive stress, the uniform compressive stress. So we call them as a squash columns. Remember, I'm sure that you remember what you did for you have already done the reinforced concrete and also the steel designs. We talk about the diagram, which is the interaction diagrams between the axial force and also the bending moment. We had the ratios between the capacity that you're looking at and compare with the squash load. So we normally use a node, and if you want to call them as a nominal capacity, so we provide them as a U and U. So what the meaning of the term at the bottom? This one we call them as a squash load. So it is the capacity of the column under the full compression force. So there is no any friction load at all. So within these diagrams, the squash load capacity that we find, we're looking at the point here. And right. And in the interaction diagrams, which is telling the capacity when you have the combination of the axial force and the frictionals, we talk about the diagram pretty much look like this. In any of the designs, we use this diagram for both the reinforced concrete design, for the steel design, and also for the composite designs, right, for the column. So what is determined by this is that when you factor the capacities, what has happened, any combination that you have sit inside the envelope, the column envelope here, so it's good. Anything that sit outside the envelope here is not good. So here is the safe design, this is unsafe. So that's why in the column design and what we're going to discuss, we have to determine how can we plot the interaction diagram when the column form the composite concrete and the steel, right? Behaviors. The first thing of all, we determine first what is called as a squash load. The squash load, I give them as a point. I call them as a point A. And the full frictional capacity, so we don't have the axial force at all. I call them as a point B. And in the interaction diagram, if you recall, we have to find, I just give you the overview first. We have to find another 2 points. Which is, I call them as a point C and point D. So if you obtain this 4 points in the diagrams, you can just simply connect the linear line, so this can approximate the capacity of the columns you're looking at. In some of the steel code, they might just use very conservative linear line like this, so it depends, right? But okay, we use this as an interaction diagram, so we need to find 4 of the point. Okay, I will discuss about the point C and D later, but everyone knows that this one, we call them at the squash load. So the squash load is mean, I just use the meaning of this. This is a pure axial force. And this one, we call them as a pure frictional force. Right. So in this 2 point, the way how we calculate, for example, for the point B, similar to what you did for the beam design. Within the beam design, we assuming that the equilibrium between the compression and the tension force is satisfied. So you have the similar tension and the similar compression. So that's why there is no any axial force left over in the cross section. The only force that developed in the cross section is just the frictional force or the bending moment. This is similar to what you design for the beam. And this one, you assuming that the full column resists the axial compression, so there is no any frictional forces. There is no moment. And in this formulation, let me explain to you what they discuss here. It is the combination of the full axial capacity that you can have for the concrete and the full capacity you can have from the steel, right? The concrete, as I mentioned before, they adjust the concrete strength. It depends on what the material you're looking at. If you look at the end cast, the end cast is mean the concrete envelope the steel section. So you drop the concrete strength by 15%. So you use only 85%. So 0.85, because the concrete didn't have the full confinement effect. Then because, and this is the concrete areas, so you take the full area as a gross areas, right? And we haven't deduct the area of the steel off. To deduct the area of the steel off in the concrete, so what you do, you have the terms here, negative minus 0.85 F prime C times AS. To get the full term of this, you should have the equation as a 0.85 F prime C times with the full, which is the gross area, the full concrete gross area should be times D subtract with the steel areas. You have the steel areas here, and you add the full strength, which is the yield strength developed throughout the steel cross section, times with the AS, right? If you do the calculation like this, it's very good, very precise, but of course the calculation will require more, right? You can also approximate the cross section by using this equation, which is still not bad, because you don't need to deduct the area of the steel out from the concrete portion, because it's quite small normally. So that's why they just said you can approximate them by using the cross section, using the 0.85 prime C times the cross section of the concrete, and then you add the capacity that came from the steel, right? You can approximate them like this, and it's still acceptable, which is not bad. There is another concept that they want to discuss with you as well. They call as a plastic centroid. This is important. The plastic centroid, it is the point where you satisfy the equilibrium under the squash load or under the full axial compression. Normally, the plastic centroid doesn't necessarily sit in the same centroid of the cross section, right? So we used to calculate the centroid of the cross section by using the first moment areas, and normally it doesn't happen that way for the plastic centroid. The plastic centroid, you have to check the equilibrium of the force, right? By we having, this is the force that comes from the concrete, this is the force that comes from the steel, and we use, let's say we use this equation from the concrete, from the steel, right? And you take the first moment areas from the top surface. We use the reference lines at the top surface of the concrete, sorry, of the columns, and you just use the first moment of areas to determine where is the plastic centroid, right? Let me explain to you what this means for the plastic centroid. I call them, this is a DPA, right? DP is a depth to the plastic centroid here, right? Normally we call this point as a PA. So what it means is that you check the equilibriums under the ultimate force in the full axial compressions, and you use the first moment of areas. For example, what it means is that we have the depth from, we make the reference line from the top surface, is it to the neutral, so to the centroid of the concrete, which is in the half. They don't put in the half because we have the steel, which is unsymmetric, right? So if you calculate the centroid of the concrete where it's left, we have it here. But if you want to approximate them in this case, right, you can assume it to be in the center of the column cross section as well. But this one, they want to make it more precise. And you have the centroid to the steel. And this one is called as a DS. And when you want to determine the neutral as the plastic centroid, what you do, you calculate the first moment of areas. You take the equilibriums by checking the sum of the bending moment about the reference lines, which is at the top surface of the concrete. I said at the top. Equal to 0, right? So what you do is that you take, not equal, sorry, you take the sum of the force. I could not draw, right? Sorry, I have to zoom in and out. So that may not make very inconvenient to you guys. But let me try to remember all the terms here, which is the sum of the force, which is a PC plus PS, time with the depth to the plastic centroid. Right, this is the sum of the moment equal to and then you can solve for the plastic centroid. So what is meant by taking the equilibrium or the equations of this is saying that when you look at the squash load, the plastic centroid is sought or is looked for where actually the sum of the force, the full compression force will act in the cross section, right? So this one we will use as the reference location where the axial force apply all the times, right? So the axial force, when we calculate the interaction diagram, is must apply to the plastic centroid. Excuse me, only, right? When you have the value of the bending moment, it will just make the couple moment about the plastic centroid. Okay, and we use this as a reference point when we want to calculate the eccentricities of the column as well. The eccentricity of the column, we made the reference to the plastic centroid. Okay, I emphasize this because we use this concept for all the story that we're going to talk for the short column design. So they give some definition of the plastic centroid here as well. The formulation I already talked to you guys, right? So you can check is through this by looking at the bottom calculation. And what is mean by looking at the squash load? The squash load is mean that, okay, as I mentioned before, we're looking at the PL axial compression force. The question that we have next is that when the steel, listen to me first, when the steel take up the compression, you can be can be weak under the compression force. So when it's weak, so what it means is can fail. When it's fail under the compression force in the local or in the section levels, so we're looking at what is called as a local buckling of the steel. When we talk about the local buckling of the steel, as what you know, right, you have to check for 3 items. One is a compact, the other one is a non-compact, and the last one is slender. Right, we have to check this all the time for the steel designs. The calculation that we use to check whether the steel section that we're looking at is compact, non-compact, and so on, we check through the ratio of B over T. must be less than to the limit, right? We have the limit, for example, the compact we use lambda, I could not remember, lambda p, I think, right? We're saying that, okay, this is a compact. So we use ratios. If it's less than or equal to the lambda p is a compact, and it is sit between the lambda EP is a non-compact, and if it sit above lambda EP, we call them as a slender sections. And if you recall to what you learned in the steel designs, if you use the AISC code, the AISC code, we have the special clause to treat for each of them, right? Especially you have to adjust your capacity if you have the slender section. In this lecture, I also explained to you, right? There are a couple of the concepts here. What is the meaning of the slender and the non-compact sections, right? But before I go through this, let me explain to you the overview of the cross section, of the meaning of it, right? When we having the non-compact, right? They're saying that in the columns, they're looking at the difference between the slender and also the compact and non-compact. So what the meaning of this is that if your section, which is you check through the ratio of B over T, B is, if you recall, is it B, T is a thickness for the hollow section. The more that you have the ratio of B over T, the more of the slender of your local section that you have. So what they say is that if you have the peeled steel and it receives the axial compression, assuming that we have the compression force, right? So it seems like you just try to looking at only the plate here. It's just like you apply the uniform compression to the thin plate, right? And they check for the buckling of the thin plate here. They're saying that, okay, the maximum capacities under the buckling of this thin plate, which is here. The thin plate is what I just take it out. And you have the uniform compression. So these sections here where I take it from this, okay? And I just take them and we put the thin plate, right? Put the boundary condition is correct. Boundary condition is mean it's got the support on this edge of the thin plate, and it's got the support on the other edge as well. So this one has got a support here. This one got a simply support as well. And what you do, you apply the uniform compressions. and the thin plate will form the curve according to the geometry effects. So this one is proven from the geometry failures. It doesn't involve with the strength at all, just the geometry purely. If you recall, right, what you learned for the buckling equation, you did it in the second years already. You're having this is the rollers. You have the pin here, and we apply the axial force, and we're saying that is go to the critical. So what is happening is that when you apply the force to the beam or to the column, which is the line column, which is reached to the critical force, what is happening is we make the curve like this. So this one we have the shortening, and it will form what is called as a lateral delta. So when we look at the equilibriums of this, you have the support, you got the force, right? And you got the eccentricities, which is equal to the deltas. This one will form, and we give to you what is called a secondary moment. And the secondary moment is equal to PCR times with the deltas. And remember, when you prove the failure load according to the geometry is mean because the column is no longer the straight line, so it's from the curve, so it's from the secondary moment here, right? You use a formulation, and that you obtain what is called as a buckling formulation. The equation that we use all the time is pi square di over L. We call as a Oehlers buckling formulation. And this one we use it all the times, but this is for the line columns, right? You can prove for the Oehlers buckling to this equation. Well, I don't want to go to the proof. It uses a sine curve and so on, and you see the first mode, second mode, and the third mode, right? If you look at the first mode, you got this equation. If you look at the second mode, you just multiply the mode number to these equations here. But if we fail according to the load, it's got the minimum. So that's why it's always fail in the first mode. It doesn't go to the second mode because the capacity under the critical buckling, it cannot go above this value because this one is a minimum to form the buckling curve. And remember, if you have the second mode, it will form another curve like this. If you have the third mode and so on, you learned it before. But we want to study the local effect for the steel section as well. So it depends on the boundary condition, which is the support of the plate, and you have the axial force applied under the columns. So when we investigate the buckling behavior of the thin plate, which is the plate here, where we got the plate here is that we take it from this, okay? And we just take it and look at it analysis. So what we can find is that under this thin plate here, it said that the buckling stress, so the stress that you can apply, and it can reach the buckling curve. So the geometry of them start to deform quite much, right? The loading that you're looking at, the stress is equal to K times pi square EI divided by the term shears. Quite similar to the Euler buckling formulations, right? This is the Poisson ratios we applied here. The B over T is the ratio of the thickness, right? The width, the clear width to the thickness. And K is the coefficients. It depends on the support condition and the type of the section you're looking at. Either it's a hollow section alone, or you look at the fill-in section. So what you can notice is this: for the fill-in concrete, this one is a hollow section alone. This is the fill concrete. So you fill the concrete in, it can delay the buckling in the steel. It doesn't only provide the confinement effect to the concrete, it can delay the buckling failure to the steel. So in it buckle, what I like to show you is this. The failure, sorry, I like slightly go a bit over time, but I'm going to finish soon. This line that I just plotted here, they put into the dot. This is the curve that sits in the envelope of the hollow section, and it's from the buckling curve. So when you form the buckling curve, right, under some of the certain load, we say that this is ineffective areas. Right, for under the slender column. Then in the calculation to adjust, just to approximately adjust the capacity of the column. So what they do in the code, in the American code, they did as well, but I don't think they explain in this way, but only this way has been explained in the Australian code and also the European code. So they explain the concept why you have to adjust into the formulation, because you have the ineffective areas that form the buckling curve. So what is mean the full cross-section area of the steel doesn't resist the force well. So they just take, okay, if you want to calculate the ultimate strength under the full compressions, they're saying that you just adjust and use only the effective areas. The area that I highlight here, we call them as effective areas. When we looking at the effective area, this one is the area that can resist the compression well. We call them as effective areas. And when we make the adjustment for the effective areas, so we remove the concept in calculating the forces, we remove this area out. We remove these areas, which is ineffective from our calculation. And we only adjust our section to have only this portion left. Right. That's why it leads to the way that we need to calculate what is called as an effective width. Right, we call them as a BE. And this is the way of the concept in both the steel and the composite designs that they use to adjust and take into account of the local buckling. So they only take into account of the effective area, and they remove the ineffective area out from the cross-section designs, right? And if you notice, what I like you to notice as well, the coefficients K is determined the buckling capacity, the more of the case, so it means the section that you look at can resist more of the force. You're looking at here with the same boundary condition, which is the two longitudinal edge have been supported, which is in this case, the K value of the hollow section alone and the K value of the composite sections, they are quite different. The composite section, they can give the capacity, the buckling capacity more than the hollow section alone, around 2 times more, right? About 2.5 times approximately, right? Which is saying that, okay, when you use the composite column, it's not only giving you the more strength in the concrete, when we talk in terms of the concrete confinement, it also increases the strength of the steel section as well, right? Because it's prone to the buckling less. So it tends to be buckled less than the steel alone. When we have the only support in the one longitudinal edge, what it means is like the flange. Remember, when we counting this, we check for the outstanding flange. And we say that this is B, and the thickness of the flange is T, right? So in this proportion, you have one longitudinal support, which is at the edge here, one longitudinal support. So when you check between the section alone with the field sections, right, the capacity is more than 5 times, right? So this is confirming that when we use the composite column, it's provide you more capacity because it prevent the local buckling, it's provide the concrete confinement to the concrete. And this is the way how we can adjust this. Remember, we only take into account of the effective section. And how we check this, we use this criteria here to check, right? And last time we discussed about this is the what we call as the buckling, the yield strength at the buckling conditions of the thin plate here. And the buckling to what we discussed, that this is for the local buckling only. We have two types of the buckling. One is the local buckling. This is caused by the slender of some part of the cross sections, and we call that the cross section didn't develop the full effective strength, and we have to do some other modification in reducing the width of the cross section, which is, I will tell you, we have the approximate method on this. And the other type of the buckling we call as a member buckling. The member buckling we will talk on this topic next week on the slender column, and this is for the stocky column. So I just want to emphasize again that when we discuss about the topic for today's, it is all about the section capacity. So we didn't have a look to the geometry of the whole column. So we didn't look in the member level. We just look in the section levels. So that's why we look at in the section levels, the thing that we use, and we classify whether the section we're looking at is it has been worked effectively or it doesn't. The way how we consider that, we consider the ratio we call as a section slenderness ratio, which is the B over T, right? I discussed about this already. B is the width of the part you're looking at. T is the thickness, right? So it depends on the boundary conditions of the section or some part of the section you're looking at here. And in this case, we have looking at the hollow section. And for the hollow section, if you're looking at into the section to what I highlight dash, what you find is that on the edge of the part for each piece of the section, it will have been restrained by the corner. Normally, if you have the plate and you weld them or you just make them as a continuous plate and you make the angle, So what it means, this angle will provide some partial support to the section. So if you run the stress analysis, as what I discussed before, you might see that there will be the fixed end stress. There will be some of the corner stress here, right? So that's why if you're looking at through the formulation to what we discussed, this is the formulation we use to approximate or to looking at how much of the stress can be applied to this thin or the thin plate with the boundary conditions here. And what's it have? This is based on the geometry only. It doesn't look at the stress and the strain curve at all. This has been derived from the geometry, right? To what I just compared to you. We learn about the geometry failures and we call them, this is the buckling failure, which is the Euler buckling condition. This is what we have learned for a long time and we use it quite a lot. In these stress formulations, what is happening, right? Just want to highlight here. We have two types of the boundary condition. One is a two longitudinal edge, which it provide the support. And if you want to see where is a two longitudinal edge, it is the edge here for the hollow section. But if you're looking at for the what is called the open section, such as the I sections, there is a case for the one longitudinal edge provide the support. And this is mean we look at the outstanding flange. But if we look at in the web, we have two of the longitudinal edge provide the support to that specific part of the section. So when we know that, the first one is a bare steel. So it didn't have any concrete involved, and the bottom one as well. So that's why when we look at the ratio, which is the K, the coefficient K, we call as a local buckling coefficient. That's be used to multiply to the formulations here. The more of the value that we have for the K, the more of the buckling, the local buckling stress has been allotted. So you might see that if we looking at for the hollow sections, we have the smaller K without the concrete at all. But if we put the concrete in the column and we form as a composite action, the K has been increased more than twice for both the two longitudinal edge and also a single longitudinal edge. So how we use this in the code, if you family, the way how we take into account the local buckling for each of the standard, they treat it in a different way, and the formation is slightly different, but the concept they are the same. The concept what they do, they try to approximate where is the areas that has been considered as effective. So the area that hasn't lose its original shape, right? For this part, to what you can see is from the buckling, and this one we call as a local buckling. When there is a local buckling, we in our calculation or in most of the standard, they treat this one has been deleted. So they try to delete this part from the section and only left what has been worked as a effective areas. So the one that I just put in the corners, this is the one we're looking at, right? And they're also saying that the ratio that they use to consider whether the section or some part of the section you're looking at is buckle, it doesn't. So the ratio that you use, they use a B over T, right, and time with the square root Fy, which is the use stress of the steel. So it's depend on what type of the steel material you're looking at, divided by 250. So the ratio here, they're based on the use stress of 250. So if you just substitute Fy equal to 250 megapascal, you will have B over T, the limit before it's formed, the local buckling is equal to 66, right? And we use this for the hollow section, for the infill concrete columns. And in the case of the belt, you use and you just do your self-fabricated and you don't use the standard section, we might reduce the limit for the slenderness, right, limit of the sections here from 66 to be 47. And there has been discussed that as well. For example, this is very interesting. You might see in this column here, we use quite sometimes But for example, we have the I section and we only fill the concrete to the side of the web. When we fill the concrete to the side of the web, listen to me carefully. So what is happened, it will provide the restraint or the confinement or prevent the local buckling under the web only. So you might see that under the flange, the top part has been unrestrained. Only the bottom the bottom surface of the top flange has been restrained by the concrete. Similarly, for the bottom flange here, the only part that has been considered as a fully excuse me, as a fully unrestrained, and it doesn't form the local buckling at all. So you don't need to check the local buckling. So that's why I put it here, no local buckling. The only part that you have to consider the local buckling, you have to looking at the flange. So you have to check for the outstanding flange. So what it really means is that you have to find what the values of the B, which is the part from the surface of the web, right, to the end of the flange, and you call them as B, and the thickness you're looking at is T. The ratio of B over T that we're looking at here, and you have to consider and you have to calculate for the effective areas for the top flange. We use the standard steel calculation. For this one here, we obtain from the standard steel books. If you have the weld section, the limit of B over T times the square root of Fy over 250 equal to 614. And if you use a hot roll, you're looking at 16, right? And if you look at this limit here, it's similar to what you have has been told in the steel code. Any code they give around the same number. Right, so it doesn't, for the top flange, the code doesn't allow some part of benefit that they have some partial confinement at the bottom or at the top if we consider the bottom flange, right? So they just treat it as a bare steel, so it doesn't have the concrete involved. So when you check for the local buckling, you use the standard calculations as what we use for the steel designs, right? And in this one here, this is the hollow the circular steel tip, right? So basically how the section is look like, you're looking at, you have one circular hollow section and you have the other one as an internal, and you put the infill of the concrete here, and the B over T has been considered by the diameters, the outer diameters, right, of the hollow sections, and the thickness T, right? The ratio that you're looking at is less than 82. So if you check with your cross section and you find that it's satisfied well with the limit that we have put on the right hand side, so you don't need to adjust your cross section at all. You can use it as a full cross section. But in the case that it sits above, then the limit on the right hand side is what you do. You have to adjust the width of the specific part of your cross section. And this one I have put some the way how we can approximate them in the next couple of the page. Before we move into that discussion, I just like to show you in the research, right? And this one we take it from the reference is Journal of Structural Engineering. Is one of the top journal that most of the engineers and the researchers they use. They believe it. And this one is the name of the author, Professor Brian Uy. Brian Uy is one of the leading professor who doing the research in the composite areas, and he's the one who taught me in this subject back 20 years ago. And later on, when I go back and join them as an academic at the University of New South Wales, and we are the good colleagues to each others. Okay, let's come back to the topics here. What I'd like to show you is that this is the limit, what it means for the buckling condition. Even similar for the member and the section buckling, we always have, listen to me first, have the curve here. So this one is just explaining that if you check and the top bar, right, this is the limit of the breadth of the width you're looking at. So B is a physical width of the section, and what has happened is that if you have the slenderness ratio of your section which is sit above than the limit, this is the limit we're looking at. The limit that we're looking at is we call them as a slenderness limit. So we say that this is a lambda. I think they call it slender. I cannot remember exactly, but you can look at the code. I think the code says something. Let me see. If you recall in the code, they're saying that we have the lambda. I think I wrote it somewhere in the note here as well. I think if we did to just discuss it before, right? Let me have a check. Yep. They're saying that they classify the section to be compact, non-compact, and the slenders. And the limit that they use is the one that we have a look here. And you can find that in the steel code. And we use which is quite similarly, except the value has been different to take into the account of the confinement or the buckling restraint of the steel. So what I try to say here is that this is just give you the comparisons. For this diagram, right? You might ask how could you obtain these formulations here? The formulation that we can obtain in the nonlinear curve, to what I just point it out. This normally we get it from the buckling criteria, right? And the formulation has been derived in a similar way to what we have, for example, to derive in the Euler buckling condition. And in the section, we have these formulations here. And we adjust the effective width of the section. And what has happened, they're saying that if the ratio of your section slenderness sit above this value, you have to reduce the width or the effective area of your cross section according to the exponentials line here. And this is in the inverse exponentials. And if the ratio of B over T is less than the limit, you can use the full cross section, right? And the one that is sit on the top, this is for the standard steel. It doesn't have the concrete involved. So you might see that when you have the concrete come and form, and they form the composite action together with the steel. So you might see that it shift the limit to the right hand side. So because of the concrete prevent the buckling in the steel, so that's why theoretically it's try to push the limit to the right hand side. So it's allow the ratio of the slenderness to be more before it can buckle, right? The reason for this is because the steel has been restrained from buckling by the concrete that envelop them. And this is the same, right? The left hand side, this is for the hollow sections, and right, let me have a, yes, this is for the hollow sections, and this is for the normally we use is for the open sections, right? And this one is for the 2 longitudinal edge support, and this is for a single longitudinal edge support, right? So that's why if you're looking at the limit here, this will be lower. Well, this is around 14. But if you're looking at for the double longitudinal edge supported, it's close to 40, and so on. And what about when we want to calculate the effective areas of the cross section and how we can approximate them, right, according to the local buckling. The way how we do is similar to what we use in what is called the steel design, right? Some other, if you want to be more precise, I tell you, we use this equation. And if you find what the steel code has been said, they say that you use this. So there are two formulations, but in the end, you should get the ratio of BE, which is the effective width, over B, which is the physical width of the section, to what you are considering. They should give very close values, either which calculation you use, right? For the first one, so they're saying that the effective width to what we are looking for is the parameters here. So what is really mean, I show you in this diagram. When it's from the buckling, the area that I will draw, as I mentioned before, in the purple, this one has been buckled, so it loses its stressness for the shape. The only one that hasn't been buckled, so it still remain their original shape in the section, is the one that I highlight in the red colors. So in this concept, what they say is that when we're looking at the total width of the section, we're looking at here, which is from the internal edge to the other side, and we call them as a B, right? And the effective width to what we are looking for, we're looking for the width that is governed by the red color, which is undeformed, and we call them the combination of this, right? This is, in this case, because it's symmetry, you're looking at this is 2, sorry, this is BE. So the sum of those two. So we want to looking at the fraction of the effective areas that still work very well. So it hasn't been buckled. So that's why the ratio of BE over T is, right, we have to find. And the way how we do the calculation of this, the first approach you use, this is the buckling stress. And how can you obtain the buckling stress? You just go back to this equation and you use this. This is quite precise method. So it means quite accurate. Right. So you use this formulation to consider for the buckling stress. There is the other way that will be much simpler. If you knowing that this is the ratio of the buckling limit, right? And the limit here is the limit that I just discussed with you, which is on the right hand side, or the value which is on the right hand side here. This is more simplified method. So what they say is that you just take the rate in the linear proportion. For example, if the buckling limit is equal to the lambda, let me think. Which one should be on top? Yes, the limit is in the lambda EY, and this is the standard ratio of your section that you're looking at is the lambda E. You just take the linear proportion and you adjust the width, right? And this is the full width of the cross section, and this is the effective width has been left over. It has to be less than or equal to B. To be more precise, you should use this formulation, and most of the code, right? Some of the code they take this. And in the Australian code, we use this one here, which is more simplified method, and it's quite conservative and so right. So you can use this one. And in this course, so I ask you to use this. How we adjust the effective width, and as mentioned before, we will take just a linear proportion to calculate the effective width, right? And the width that we're looking at is, once again, is an area that still has been undeformed. And how we find this? This is my handwriting. The way how you do the calculation is this: the area that still has been considered as an effective is the one that I just put the red lines here, and so on, right? So you use this formulation. So we call this one as an effective zone, and you're just looking at the linear proportion. B, when we consider, you don't forget that B had to be the internal. You start from the inner surface, which has been unrestrained, and the space between the length between the unrestrained in the part of the section, this is B. And similarly, because this is symmetry in X and Y directions, so when you do the calculation, you do the same for this as well. And if you want to calculate the effective width, so what you do, right, the combination, the combine between these areas, the width of this and the left part and the right hand side part, it is equal to BE. The BE is the ratio of, it's a fraction, which is in terms of, one thing is you use this formulation, but to what I'm said that in this exercise, we ask you to use this one here, okay? So what does it mean? If you want to use this bucketing formulation, you can do so. But in our calculations, once again, I ask you to use a simplified method. So you don't need to use, if we give you around the same number, right? So we take this into our calculation and you just adjust and you find the value of BE, right? Which is the width, the combined of two width here. And you can do, because if you have the gap in the section, is quite hard when you draw when you want to trace the stress and the strain diagrams. And because in later on, we had to calculate the draw, which is called as an interaction diagrams. And if you leave them as a gap here, it will be quite difficult for your calculation. For the top part, which is the one here, is not too bad, which is we have to treat them as ineffective areas. So in our calculation, we treat them as a void. In our calculation. So when you have to do the stress analysis, so basically you look at the strain, right? And you try to change the level of the plastic neutral acid to each other very well. And then you can draw the stress diagram. And if there is a gap here, the calculation will be more tedious. The simplified method also giving you the way how you can just do it a bit more simpler, a bit in a simple way. So what they ask is that you can just lump them, so you just sum them together. The top part and the bottom part here is just simply that you just take the areas, these two areas, and you just sum them and you leave them in the middle. Because when we're looking at the combination of the axial force and the bending moment, we only look the bending over the x-axis here. This is an X and this is a Y. So it doesn't matter. It doesn't matter whether when we calculate the bending, when do the calculation over the bending mx, it doesn't matter whether these two areas will be stay together or will be split apart of this, right? For the web part, which is at the vertical part of the sections, rather than you leave the gap here, the code suggests that you can do the simplifier way. So you just take the effective thickness. How to calculate the effective thickness? Because you knowing that the total areas of this, right, the of the effective zones. Let me see. So you're knowing that the total area of the effective zones right? And how you can find the total area of this? I don't want to mess up in this diagram here. It's this one here, right? So it is the total width, which is B, subtract the two thickness, which is 2T, and you time with the effective thickness. So you will have this one here, and it is equal to the total width, which is the total width. You sum the width for these two and time with the real thickness. So what we use, rather than we use these areas in the calculation, we tend to use the one here, which will make your calculation is simpler, right? And because we just looking at the what's it called, the bending about the x-axis, so it doesn't make a difference. So what we do, we use this formulation. All right, and what I like to talk as well, just to wake you up. I used to teach the concrete back when I was at New South Wales, and I used to give this. Let me show you. I used to give this as a exam question. No. That's okay. I use my hand dry. And how the question is look like. This is the girder. So we have the wall here. And I make it even more complex. So what I do, I put 3 of the web or 4 in my examination. Make it wider. And this is a girder. And in my concrete test, so what I asked my student that time, can they find the bending capacity, which is MUX, as a nominal capacity of this beam, right? Believe it or not, not half of the class can do these exams because they're not familiar with this shape of the cross sections, right? When I ask about, okay, can you find the bending capacities of these cross sections here, and they're not familiar because most of the student has been taught that They can calculate the cross section of the rectangle. They can calculate the cross section of the T shape and the eye, right? But they are not being told how to calculate the section of the girder, right? But in fact, if we ask in this problem that can you find the bending capacity about x-axis? In this diagram here, this can be equivalent to what I'm going to show you. Not nice. I just use, if you use the equivalent areas, you can do this problem. And how we said the equivalent areas, the area with the width of the section is still the same. It doesn't change, right? Sorry that I didn't make it to the scale. So this is the width of the cross section is still B. At the bottom width as well. But the only trick is that you looking at the thickness. This is T, right? And assume it has the same thickness. You just have to transform the girder to be the I shape with the 3 times of the thickness. And you can do the calculation. And this is back to what we are most familiar with, which is the I section, right? And believe it or not even half of the class can just use, can see this concept. So what I try to say is that we can have, this is in the real cross section that we're looking at, and we want to calculate the effective areas where it's work under the buckling, right? Rather than we use these diagrams, it really quite tedious because when we looking at the effective areas, you will have only this part in your calculation. And you want to find, if you want to find the bending about the x-axis, or a y-axis, you will have the problem because there is a void, and we make your calculation is more tedious, right? If you remember what you did for the concrete design, what you did for the standard steel design, you have to vary the level of the plastic neutral acids from the bottom, right, up to the pure bending, which I'm going to talk next. And when there is a void, it will make your calculation quite tedious, right? So that's why we suggest you to just transform these diagrams to be the one at the bottom. So it will make your calculation much easier, right? Just keep in mind on that. So what I suggest, please use the effective thickness rather than use the effective width for the web part of your cross section. But for the top part, which is the top and bottom part, you can use the effective width, right? And this has been told here. Okay, now what we do next is that we need to approximate the capacity of the column. We look at the section capacity. The idea to calculate the section capacity, let me show you, this is the diagram we look for, and we call them as an interaction diagram, which is similar to what you did in the reinforced concrete designs, the post-tension, the pre-stress concrete designs, or the steel design. The composite is the same, you need to find a couple of the point in the diagrams. The combination is that you plot the curve in which on the y-axis, we call them as a bending capacity. And on the x-axis, we call them as a, the axial force capacity. And this is the bending capacity. Because when there is a combination of the axial force and the bending moment or the frictional forces, what is happening, it will drop the capacity of the axials, which is the axial force to the column. And the way how it's drop the capacity, it will drop according to the nonlinear diagram as is. There are two ways that you can calculate these diagrams. The first one, if you want to make it more precise, you have to run to what the concept is called as an elastic plastic behavior, right? Let me explain to you what it means for the elastic and plastic behavior. But if you want to use the concept of the elastic and plastic behavior, you have to keep changing or vary the level of the plastic neutral axis. When we talk about the plastic neutral axis, what it means is that you keep, for example, if you put the level of the plastic neutral axis, sorry, not the plastic one, this one is an elastic plastic, so it's not a rigid one. So we call them as the neutral axis. So what the meaning of the neutral axis, remember for the beam, if you recall for what you have for the beams, to what we just learned before, we say that the neutral axis is, we started from the centroid, and we keep vary the value of the strength. And how we do the variation of the strength, so we start from the strength so small, and we keep bend, right, the cross section. The more that you try to shift the strength, or you try to bend, or you try to form the curve wedges, right, the more of the strength you have in the diagram. The more the strength you have in the diagrams, it will involve with the more of the stress. In the beginning, you may have the linear stress, and it will reach up to, you have the non-linear stress behavior. Right. So this is the stress. Similarly, for the elastic plastic, what you do, we need to do the variation of the strain, right? And the strain that we're looking at, we limit the strain in the concrete up to the ultimate strain, not the ultimate, the ultimate strain that we allow in the concrete, which is 0.003, similar to what you did for the concrete designs, right? And what is happened when you have the strain curve? So this will tell you how the curve is look like. Based on the information of the strain, right, you can have the information of the stress. In the concrete, the stress diagram pretty much look like this. Right, and we use, once again, the equivalent rectangular block areas. This is similar to what you learn in the reinforced concrete designs. So what we do, you have to adjust the values of the maximum compression stress in the concrete. It depends on whether the concrete has been fully confined or hasn't been confined, right? And in this case, because we have the encased steel, the steel is inside, the concrete is outside, so we use it 0.85, so use only 85% of the efficiency. And for the depth of the rectangular block diagrams, you have to find the value of the gamma, which is to adjust the ratio to the neutral axis depth. right? The gamma calculation is similar to what you use in the steel, but had to be less than equal to 0.85 or less than 85%. Right, by doing this case, you can approximate the stress diagram of the concrete and you can find the total force under the area of the concrete stress. But for the steel, so you have to draw, you have a look here. You draw the diagram for, not the, sorry, this is not the steel. This is for the concrete. Because we have two materials, you have to draw another diagram, which is the stress diagram for the steel. So based on this value, so you use based on this strain diagram again, and you have the steel which is encased inside the concrete. You have to find where is the yield stress in the steel, and in the level of the the yield strain. And how we find that is this: you just use a linear proportion. For the strain diagrams, how we calculate the yield stress is this. Remember, can I just delete this? Remember that we having, and we always use the stress and the strain diagram here. And we knowing that this is for the steel, we have the very nice linear proportions and the flat curve. And what we know as well, the Young modulus of the steel, it is equal to 200,000 MPa. So it's depend on the yield stress you're looking at. If you're saying that this is the strain at yield. So what I say is that if the yield stress, it is equal to 400 MPa, the strain at yield, you can use a linear proportion calculation, which is equal to the yield stress divided by ES, that we're giving you 0.002, right? And based on the value of the 0.002, for example, in this case, you just use a linear proportion because you already calculate the neutral axis depth, right? So you just use a two similar triangle, which is one is a big diagram, and the other ones is the diagram over here. Right, and you find that, okay, when it is the strain value is equal to the yield strain, you just find the linear proportion to the depth here, which is equal to NA times with epsilon y divided by 0.003. So you can calculate for the level where it's developed the yield, right? And anything that have developed the strain above than the yield strain, basically the stress diagram reforms as a perfectly plastic stress. you have this equal to the yield stress. The rest of them is just the linear in the triangle, right? You have the maximum is equal to the yield stress. The rest is just a variation of the linear lines, right? Having the width of this. This is time. So what we do in this case, you're looking at in the steel. In the compression part in this diagram, if we have the compression force, which is coming from the rectangular part, and also another compression force based on the what's it called, the triangle part here. And in the bottoms, you will have the tensions based on the stress, which is coming from the triangle stress diagrams. Everything you just stick to the linear line of the stress. So at the bottom may not reach the yield stress, right? So the stress at the bottom in the steel is still less than the yield stress in this case, right? So we keep doing this. So if you know the stress and so on, what you can do is that you can sum the value of the force, which is the area inside, and don't forget, when you're looking at the shape of the cross sections, you have to split them, which is quite tedious, right? But just listen to me first. We have another way which is much simpler, that is still acceptable. We have to split them into this level. Every time it change the cross section, we have to calculate the new areas to what I discretize them. And this is at the neutral axis line. So you might see that when you're looking at into the stress diagrams of the concrete, you time with the full part of the concrete, which is this area here. So that can give you the force according to these areas, times the stress, which is 0.85 times F prime 6. When it comes to the flange part of the steel, the area of the concrete will be left only this small piece. And you use these areas and time with the value of the stress you have in this diagram, which is 0.85 prime 6. When it goes to the red part of the steel, the area of the concrete will be two rectangle. This is one. And the other ones, let me adjust this. All right. And there is the other part. Right, and you time with the areas. Not that time with, sorry, time with the value of the stress, and this is the area. So you might have, we have so many different areas, which is might be the A. In the concrete, we have the A1, right? You have the part of A2. Let me And when we look at the areas, we have the area, the value of the area A1 in the flank is A2. In partials of the web is A3. And you keep doing this. Right. And you only calculate the area of the stress up to, I have to take this off. This is wrong. Up to the levels here. That's all right. So you only calculate the areas and time with the stress value. So in this, when you have the stress time with the area, you get the compression force, but you have three different value of the areas that you use, and that can be calculated for the sum of the compression stress, so the compression force of the concrete. And for the steel, it's even more difficult because you have the non-constant of the stress developed in the steel, and this one is in the triangles. So what you do, you have to find first, based on the top flange in the steel, and normally for this we develop what is called the yield stress in the top flange, and you find some part in the web of the steel where it still develop the yield stress, right? I didn't want to draw the line and keep running the line through. Let me see if I can do something. Right. So this little area in the web is develop the yield stress in the web part of the steel sections. And once it happened at the bottoms here, is now develop the stress according to the triangle areas. So you have to find the triangle stress times the areas here. Okay, we need to fit the thickness of the web part. And similarly, you do for the bottom to get the tensile force. So that's why you have so many forces in the steel. And once you calculate all the components of the force that has been developed in the steel and the concrete and the steel, of course, the forces, you can just take the bending. Listen to me first. You have to take the bending, the sum of the bending about the plastic centroid, right? When we do the calculation of the bending about the plastic centroid, you will have the capacity of the bending moment. The capacity for the axial force is quite straightforward. You just sum the compression and you subtract to the tension that developed. Sorry, this is the compression force, and you subtract with the tension that developed in the steel. And whatever is the resultant of the summations is give you the capacity in terms of the axial force for the columns, right? So you might see that if you have to perform the elastic drastic, the thing that you need to know first is where is the neutral axis depth. The neutral axis depth is normally has been told. So what normally people do, they keep varying the neutral axis depth they keep varying the neutral axis depth. For example, if you write the code in the Excel, you can simply just raise the level of neutral axis depth from the bottom. If the neutral axis depth at the bottom, so what it really mean is similar, it's very close to the full axial force capacity, because most of the cross section will develop the compression force, right? And you raise them up, right, until it reaches the pure bending. So we keep raising up the neutral axis depth, right, and varying them, and then you keep calculating. And remember, this is very important, is that the level, the centroid that you're looking at for the calculation of the eccentricities, it is we're looking at about the plastic centroid, okay? And this we use into the calculation for the frictional capacity and also the axial capacity, right? We always refer to the plastic centroid. The axial force have to go to the plastic centroid. When there is a moment, we say that there is a eccentricity. The eccentricity is far from the plastic centroid. And if you had a symmetric cross section, the plastic centroid will sit in the center of the depth. Okay. So based on this concept, right, and if you read through, they will keep saying this, and for the encasted, listen to me as well. For the encasted, don't forget 0.85, right? But if for the, what's it called, the infill concrete, so the concrete has been enveloped by the steel tube, you can use the full capacity of the concrete. So we don't need to use 0.85, we just use F times the stress away. Right, but the way how we calculate the neutral axis depth and so on, we have to do, because this is the elastic plastic analysis. So it is a combination of the elastic and the plastic stress. Before we move ahead, any question on this first? Do you have any question? Please feel free to ask me. If you don't, so let me continue further. And what has happened is that when you trying in this diagram, what is trying to say is this: if I fix the plastic centroid, right? No, sorry. If I fix the neutral axis, right? I fix them because this has been given. Normally, the neutral axis has to be given. In our calculation, right? And if we fix the neutral axis, and what we do, I trying, right, with the same neutral axis, I trying to bend the section of the column. So the more that I bend the section of the column until it reached the ultimate, right? So it starts from this, and I keep bending them until it reached the ultimate strength that we allow to develop in the concrete. So the more that we keep rotating the cross section above the neutral axis, right, it will giving us the point in the curve here, right? Because we plotting the graph between the curvatures and the bending moment. When we running the stress analysis, by keep changing the value of the curvature, once again, what it means, this is the curvatures, which is the angle, how it's rotated. And we start from 0, but we keep rotating about the neutral axis, which is we fix them. The more that we rotate before it reach the ultimate, what is happened, the more of the bending and the axial force capacity is keep increasing, right? So that's why we can plot the graph, which is based on each of the neutral axis. This is for example, for the neutral axis 1. And this is for the neutral acids too. Then we fix them. And the last one is a neutral acid 3. Right. For each of the given neutral acid step, so we don't change the neutral acid step at all. And once again, we keep just rotating them about the neutral acid from 0. When it's from 0, so it doesn't have the strain in the cross section. When it doesn't have the strain in the cross section, we start from the 0 point in the diagrams. The more that we keep rotating the neutral as rotating the curvatures about the neutral acids, right? If we start to bend and apply the axial force to the cross section of the column, what is happening? The capacity will rise up to this level here until it reaches the ultimate. When it reaches the ultimate, what is really mean at the ultimate? When this it happen? When the epsilon cu equal to, which is the strain in the top surface of the concrete, equal to 0.003, and then we stop, right? And what has happened when it reached this level? So it's seen that we obtain the ultimate capacity of the bending, and of course, we can obtain the ultimate value of the axial force as well, right? So we keep collecting the informations. In this case, we have the values of the M chart, and we have the capacity for the N chart. Right, and this is we stop them. And this is belong to 1. And for each of the neutral acids level that we're looking at, we can obtain the ultimate point. And what we do for this ultimate point, we keep collecting the values which is a capacity that we can calculate from the section analysis, and so on. Right. And we taking this point, listen to me first. We taking this point and we plot into another diagram, another graph, which is the capacity. This is the ultimate capacity. In terms of the axial force and also the bending moment. But in the diagrams, how can we have different value of the ultimate capacity for the bending and the axial force? Is we have to vary the curvature. So we have to vary the neutral acid step. So in this point that we have from the PL axial force, up to the pure bending, we keep raising the neutral axis step. If I take the diagrams in here, we keep raising the neutral axis step from one starting from the bottom, and we keep moving them up for the different level of the neutral axis step. So when we vary the neutral axis step, what is happen? This might, for example, this might giving me the neutral axis depth number 1. This might be the neutral axis depth number 2, number 3, and number 4. So we kept raising up the neutral axis depth, and this one is the neutral axis. I put it here as a NA. And so on. The more that we change the level of the neutral axis, if I say that, okay, the neutral axis depth is at number 1, the higher of the neutral axis depth is the higher value of the bending moment capacity, and it will be the less value of the axial force capacity. So that's why at the ultimate point, you may have this value, right, as the ultimate point. When you try to lower the neutral axis depth to the point 2, you will have the lower value of the bending moment, but you may have the higher value for the capacity of the axial force. This might be at the point 3, and when it reaches point 4, the bending capacity is close to the flat, so it's close to 0 because you have the pure axial force capacity or the squash load capacity. So that's why what I try to say here is that when we varying the neutral axis depth, so we starting from this point, you may have the neutral axis depth at the level of 4. This point, you may have the neutral axis depth at the level of 3, 2, and the last one is 1. So if you keep changing the level for the neutral axis depth, you will have the different capacity for the ultimate bending and the ultimate axial force. So based on this value, right? Because when we vary the neutral axis depth, so we try to have, for example, if in the point number 2, so you just try to rotate the cross section about the neutral axis depth, right? And if you keep rotating, so you keep increasing the curvatures about the neutral axis depth. So basically, you keep trying to trace the capacity up to the ultimate point. And the capacity at the ultimate point here, for example, if we're giving you the capacity in this diagram, right? So this we obtain from the ultimate capacity, and we take the ultimate capacity and we plot in our interaction diagram. So that's why the meaning of the interaction diagram, so is give the envelope of the ultimate strength at any possibility of the neutral axis depth, and also the curvature that it reached the maximum capacity for that neutral axis. Right, this is the meaning of the interaction diagram. Okay, so it's collecting the information, which is the capacity of the beams, or the column which is the combine between the axial force and the frictional force, and this is the curve you have here. If you keep varying the level of the neutral axis depth to be fine enough, right, you may start from the bottom, so you may have the point somewhere here, and you keep increasing slightly, you will have the smooth curve, which is as a dot one. But if you just take some of the point, which is I going to tell you which point you're looking at and what the code asks you to find for, you just start to look for a couple of the point to represent to approximate in the safe size the interaction diagram, because you cannot do it by hand unless you have to put into the Excel, so you can get this nonlinear diagram here. We call them as a nonlinear interaction diagram, right? So what we do is that in the code it says is good enough if you can just connect the curve between point to point. Right, and this is what we're familiar with. And when we check whether the section that we're looking at is safe enough or not, we're saying that anything that sits inside the diagram here, we call them as a safe size. It's certified, it's good. But anything that sits above, so it sits outside the diagrams, we call them as an unsafe design. Right. The concept is similar to what you learned for what is called the steel or the concrete. You have to draw the interaction diagrams. Before we move ahead, any question first, please? Feel free to ask me. I try to describe in the best way I can do. So, but I'm not sure whether it can answer your question or not well. So if you have a question, ask me first. Nope. Okay, if you don't have the question, so let me move further. If you want to get it more precise, the capacity to be the most correct, so what you do, you have to obtain to perform the elastic plastic, but it's very tedious. You see why? Because you have to check first the smoothness in the stress diagram, the smoothness in the area you're looking at, the smoothness in the stress diagram of the steel, right? Some part of it might be some part of the top frame that still may be yield, some part it doesn't yield, and so on. And you have to mapping them to each other level, and so on, right? So this is quite a tedious process. So this is not nice. So let me delete it. So this is quite tedious process. So it's take a lot of time, unless once again, if you put in the Excel, it's really easy because you can just put everything in terms of the parameter and you keep varying the parameters, right? And it will work that way. That's why the code allow you to assume that the problem you look at is ductile. Ductile is mean it can develop the full strength, the ultimate strength. So we're looking at the concept of the rigid plastic, similar to what we did for the beam design. We use a rigid plastic. Remember that? In the concept of the rigid plastics, so we still need to varying the level on the neutral axis there. For example, have a look here. The stress diagrams, the stress value here, I think, let me have a look. We have 3 components. Listen to me. Then let me check you one, talk to you one by one. The first one is a concrete. The second one is a steel, which is the steel structures. And the last one is a rebar, reinforced concrete bar. Okay, or I put the steel bar there to be short. So you might see that when we discuss about the assume that to be the rigid plastics, so the stress developed in the cross section for any tile of the materials will reach yield or reach the ultimate point, right? In the concrete, if it is an encasted, we allow up to 85%. For the steel, we allow up to the yield For the rebar, we around up to the yield of the rebar. Why we have to say that the yield stress in the steel structure and the rebar can be different, because normally the rebar is a high strength. You look at around 400 MPa. For the steel, you look at around 300 MPa. So that's why we have to split the diagram. So we normally don't combine the diagram. And we try to vary the level of the neutral acids to what we have described to you in this diagram here. And how are we doing that? Is as follows. If I like to obtain, let's assuming that I like to obtain the smooth curve, which is the curve over here. So what I do, I have to start from the level which is called as the pure axial. When it's saying that it's a pure axial force, to plot them in the graph, which is representing the ultimate strength for the axial force and the bending in X and Y. So we're saying that, okay, in this point of the graph, we have 0 in the bending, and we have the squash load for the axials, right? And where the neutral acid step responding to this point, basically, listen to me, basically the neutral acid step responding to those points is sit, it doesn't sit here, it might sit somewhere here, sit much above, just beyond the boundary of the diagrams, right? So that's why you can have the rigid plastic in the curve develop in the cross section for all material as a full, right? But to make it to be simplified, we say that it's at the bottom, and we say that the curvature has been developed so much, right? So that is allow the stress to develop the full capacity, which is the full yield stress or the ultimate strength capacity in each of the materials. So we say that the neutral acid step here is at the bottom. And we call it is at the point number 1. So that's why we say that this is corresponding to for the neutral acid step at the point number 1, right? Coincide to what? Sorry, I said point number 2, 4. Say 4. Because we need only 4 points. And what we do, right, after this, we keep lower the neutral acid step, and when we lower them, no, we not lower, we have to raise them up. When we raising them up from the bottom, we go somewhere here, and we saying that in this level, the neutral acid step is corresponding to the point number 3, and where it is the one here, which is at and we keep raising up, so we get the point number 2, which is the one here, not here, which is right in the plastic centroid. And I made the comment that this is at the plastic centroid. So where it is here. And the last level of the neutral acid step is where you're having the pure bending capacity. This is at NA1, where you have the pure bending capacity. So I say that in this level, right? When you plot in the graph, you have the M, which is the ultimate strength, and this is none. So we have a couple of the points from, right? Sorry, it didn't go to the order. When at the bottom, you raise them up to some level. So you got the point here, you raise them to the process control, you have the point here, and you go up to the pure bending, you have the bottom point. So you might see that to what we discussed in this diagram, we only look up of the point that can represent in these boundaries, right? And it's got the meaning. When we discussed it, if you want to try, for example, you can try, if you can develop in the Excels, you can find the immediate capacities when you have the neutral axis step sit between, for example, the bottom surface of the column and at the neutral axis depth 0.3. So you might have the neutral axis depth somewhere here. You just rest in the intermediate value between these two levels. You would have the strength somewhere here. The more that you raise up, you keep higher the neutral axis depth up, the more of the bending capacity you will find, but the less of the axis capacity will drop, right? We go down. So you can have the choice, either you want to obtain the fully nonlinear, right? You have to have so many calculations. To what I suggest to you is to use what is called the Excels that can help. Or you can just have a couple of the point and just draw the linear line and connect them. We call this one as a nonlinear curve, because it's nonlinear on the diagrams. And we call the other one at the bottoms as the piecewise linear. Right? Because we approximate the nonlinear diagram by using a couple of the points in the nonlinear, and we just connect them by the linear line. That's what we call piece by piece linear, or the piecewise linear. The code says that you can just take only 4 points and you can check it, right? You don't need to get the full nonlinear diagram. What I ask you is this: I will load up the assignment number 2, possibly on Fridays. I already write them up. And the problem that we ask you about the design of the column, which is the section and the member design. But this week we talk about the section design first. And then we ask you to draw the diagram, which is interaction diagrams for both the nonlinear diagram and the piecewise linear diagram, right? The nonlinear, you have no choice. You have to use the Excel to help. But for the linear diagram, you can use just only 4 points. Okay. Okay, let's come back. And how can we obtain for some of the point in the diagrams if we use the concept of the rigid plastic? Definitely, from what we keep talking from the beginning of this week, we talk about the squash load. The squash load, we get this one here, which is the full axial compression. In the last couple of weeks, when we're talking about the bending capacity, so we check the equilibrium that the sum of the forces in the cross section, the compression force and the tensile force has to be equal. So it's just balanced then well. So it doesn't have the axial force left over. That in that sense, we have only the bending capacity. And this point is similar to the beam design. Right, between the full the squash load, which is the axial force compression, and the full bending capacity without the axial force at all. The intermediate level, which is where you're having the neutral axis depth vary between the point number 4 and the point number 1, which is the level of the point number 2 and 3, or the point C and B, right? In this intermediate value, so we tell you how can we have these two and what the meaning of this. So when you calculate the interaction diagram, the first thing you have to calculate the full pure compression force. The second point, you have to calculate the full bending capacity by assuming that the compression force and the tensile force, they are equal, right? So that's why I just make the comment here in this point, the sums of the compression equal to the sum of the tension. So that's why you would have the NO equal to 0. But in this case, you have the tension equal to 0. You only have the compression, which is equal to the ultimate strain, which is equal to the sum of the compression, and MO equal to 0. Right. So you have to identify these 2 points first. Okay. Then the intermediate point, which is the point, the level at the neutral axis number 2 and 3, we're going to the neutral axis number 2 first. The neutral axis number 2, you calculate at the level where you have the NA2 is at the plastic centroid. You just need to calculate where the plastic centroid is, and how we find the plastic centroid, right? You have to go and look for one in the pure axial force. At this level, where the total, the sum of the forces has been applied, you will have what is called as a plastic centroid. So if you have the neutral axis depth sit in the same level as a plastic centroid, so what has happened, you will have the point number 2, which is here, right? For the point number 3, which is the last one, which is at the point, this point, which is the point C here, the neutral axis depth have to sit lower than the plastic centroid, but at the proportion between HA and HA. So what is mean the HA is this? The HA is a distance between, first, this is the neutral axis depth that you can have when it's formed the pure bending, which is at the point number 1, and the distance, which is at the plastic centroid. So in this case, you will find the difference between these 2 levels, and we call them H and Hn, right? So what is mean the Hn when you calculate the for example, at the pure bending, you obtain This is the DN. And this is at the NA. NA. The HA, HN is a difference between the D and A, which is the depth to the neutral axis, the plastic neutral, the plastic centroid, subtract to the neutral axis depth that you obtain from the peel, bending. So you take these two values and you just find the difference between them. You got the value of HN. Then you allocate, right? You allocate the plastic centroid at the neutral plastic neutral axis, sit below the plastic centroid at the distance of HN. So this you will obtain the point NA3, right? Which is giving you the point C is over here, right? So you just need to find 4 level of the neutral axis, plastic neutral axis depth. First, when you have at the bottom, you can calculate where is the plastic centroid, right? This is what we discussed before. This one will give you the squash load. Second, you just calculate by using the equilibrium equation, the sum of the compression equal to the sum of the tension. That will give you the level of the neutral axis depth, which is dn here, based on the peel bending. You take the difference between the plastic centroid and the neutral axis depth for the peel bending. You will obtain the value of Hn. The Hn will tell the intermediate point between A and B, which is at point C and point D. The point C you can have is when you raise the neutral axis depth from the bottom surface to where you have the level of the neutral axis depth, plastic neutral axis depth. Just sit below the plastic centroid with the value of Hn. The point D, you just raise the location of the plastic neutral axis depth to be at the level of the plastic centroid, right? This is also the level of the plastic centroid as well. So you get 4 location of the plastic neutral axis, neutral axis depth, and then based on this, each one of them, anything that sits above the neutral axis depth will form the compression stress. For example, we have this compression stress here in the concrete, in the steel beams, and in the reinforced bar, right? So that's why at point A you have the full compression force, because everything is go to the compression. At the intermediate point, for example, you raise the neutral axis level at 4 to be 3, so you raise them from the bottom up to this level. So as I mentioned before, anything that sits above the plastic neutral axis will form the compression force, compression stress, sorry. Yeah, so you have this. And anything that sits below will form the tensile stress, right? And when you raise them up to the neutral axis point number 2, so what you find once again, this is where the compression stress is. And you have them where the tensile stress is. Okay. And what you do, you just use the same concept by taking, right, up, this is up to the maximum bending capacity, sorry, up to the pure bending. This is the last point. So based on this, each of these stress diagrams, so you just use the stress time with the areas for the proportion of the material that is involved. For example, this one is the concrete, right? You have the steel and you have the bars. Time with the area. So the stress area, time with the area of the material or the bit of the materials. So what you do, you obtain the force, either in the compression force, you know the centroid of the force, each of the force component. You can get the sum of the force to get what is called the axial capacity. And then you take the first moment of areas, right, to calculate the bending about the line, which is what we refers to the bending that we discussed, that we always refers to the plastic centroid. Okay. So you calculate the bending about the plastic centroid for each of the diagrams that we're giving you back what is called the bending capacity. Right. So before we go ahead, any question first? So we know the concept how we can obtain the point A, B, C, and D in the interaction diagrams. The calculation, I have the example, which is I'll just skip this through first. In this example number 1 and example number 2, right? So you can just go and have a look at them. And the nice thing of the example number 2 is this. This one, they're showing you that, let me have a look. Okay, this is the non-slenders. Do we have the slender section? Nope. This is ought to be the compact section, though it's no slender. That's all right. This is all compact. Okay. All right, so we had 2 examples at the end. And what I like to talk with you just before we finish is that if you try to use just a geometry of the stress in the diagrams here, you can find some things which is helpful. In this diagram, you're seeing that everything is developed the full compression stress. So that's why it's no doubt why you have this point. But when we look at here at the point B, you're seeing that this is the stress in the concrete, this is the stress in the steel, and so on. When you have this pattern of the stress, what is happened, it will give you the zero axial capacity, but it's give you the max, the bending, which is the pure bending as point B. But if what I try to do is this, hold on. And if we, what we try to do is that if we look at the point number C, right, you see the proportion of the areas. I'm not sure, is it, let them, hopefully it's help. If I look at the proportion of these areas, it will be the same, it will be similar to this proportion of areas. Did you compare between these 2 diagrams? And what you find as well, you have this, the thing that is different between these 2 is you have another proportion of area here. Right. So if we use these two diagrams and you compare between them, right? In this diagram, we have this in the compression tension, this in the compressions, this in the compression, and so on. For the steel bar, right? The combinations of the tensile force, so the compression force and the tensile force, they are the same. It doesn't change. But for the steel structures, the portion of the compression in B is less than the portion of the compression in C by this amount, right? And we have this add-on as well. So that's why if you do the looking at the comparison between the geometry of the stress diagram, you will find that by comparing the point B, you just go and check, and point C, right? You will have the similar value of the bending capacity, but you will gain more what is called the axial force capacity by raising the level of the neutral axis to this one here. But if you drop this by half, half is mean half of 2hn to reach to the neutral axis step, to the plastic centroid at point number D. What you will find is that the capacity of the axial force will drop by half. This is the relationship between this combination. You can go back and have a check by using just a geometry of the stress diagrams. If you drop by half, why the reason is drop by half is because in this, right, we have the unbalanced, that if we compare between the axial capacities, right, this will be the same, but this will play part as a compression. You have more compressions here. But in these diagrams, the amount of the compression in this diagram is the same, right? Sorry, it's reduced by half because you lose the proportion. Hold on. I have to compare them. Let me see. You lose a proportion. Okay. This is a proportion to be talking about. You lose this in the concrete, you lose a proportion of the compression force by half, but in the steel, you lose it by half as well. So that's why the axial force that you're looking at when you compare the geometry of the stress diagrams is give you the relationship that if you can obtain whatever the axial compression force at point C is equal to M NMO, at point D you will have only half of it, right? Because if you compare the proportion that I just write them in the gray lines, right, and you can check it. This is in compression, but it's in compression, and this is in tension. You see that in this diagram you lose by half, right? So that's why you lose the axial compressions by half. This is just to explain to it, right? And the rest of it. So what I like you to do is that we cannot go through all of this, but I just ask you to look at the example number 1 and 2, right? And into this slides here, what is telling you just two very little different is that if you have the encasted sections, you are allowed to use the concrete compressive stress up to 85%. But if you look at the concrete infill sections, you can use it up to 100% of FC. This is the thing that's different. So what it means, you might notice in the example, the only difference between the infill and the encasted is this. In the infills, they use the axial force capacity in the compression, which is the compression stress. just to the maximum, which is the 50 MPa. And also, we also suggest you to use the equivalent rectangular diagrams, right, to make the calculation much easier. So this has been explained in the example, right? So what I asked you to do after the lecture of this week, can you just go through to what they explained in the code is similar to what I just described to you, right? Except the thing that we haven't mentioned is that when you talk about the infills, you are allowed it to use a full compressive stress up to F prime C because of the confinement effects. Allow to adopt the full F prime C as a result of concrete confinement. Infiltrated. Okay, so I just give some little comments here. So the rest of the calculation the same. So what you need to know is you need to know where can you obtain the squash load, the full bending, and the intermediate point, which is at the level of neutral axis step 3 and 2, right? And what I ask you is by using this simple diagram, you can see the relationship between the point C and D, in which you will find that the bending, the axial force capacity will be half in D compared to C, right? And if you're looking at the comparison between these two diagrams, you'll be seeing that why at this point you have the zero axial force, but you have the bending moment equal to MO naught, right? But at point C, you have the similar bending capacity, but you have some of the axial force capacity as well, right? Just by looking at by the graphical comparison between these 4 diagrams. Okay.